Even though it was not the problem voted off the island, I'd like to go over problem 12 because it's the first time we've had magnets in a problem. And as I work with individuals on this problem, I see that many of you are struggling to get the correct free body diagram. Now again, if you don't have the correct free body diagram on a problem, you really are wasting your time with the rest of the problem. There's no points to be had there. And so we need to be able to follow the recipe. Now, in this case, we're told that the mass of the business card is 25 grams, and the mass of the magnet is 50 grams. Now, folks, if you get a mass in grams, you can't use that in any of your equations. We use kilograms in our equations. And so I've got to convert that to kilograms by moving the decimal place 3 places to the left. So that's going to be 0.025 kilograms, 0.05 kilograms. Now let's draw the free body diagrams. We always start with the free body diagram of the simplest object first, the thing that is touching the fewest other objects. In this case, that's going to be the magnet. Now, the first force I put on any diagram is the gravitational force Earth on the magnet. Now, that's going to be the mass, which is 0.05 kilograms, times the gravitational field strength, 9.8, call it 10 newtons for each kilogram. And that's going to give me half a newton. Now, many of you just took the 50 grams and multiplied by 10 and got 500 newtons. That should scream out at you. I mean, it's 5 newtons to a pound, but that's a 100-pound refrigerator magnet. That's massive. You don't want those on your refrigerator, okay? Now, the next thing I do if I follow the recipe is I ask, are there any magnets in this problem? Finally, yes. Now, here's how you deal with magnetic forces. The magnet and the refrigerator are attracted to each other. They're attracted to each other. One of those forces is to the left, and one of those forces is to the right. But I don't care about both of those forces. I'm drawing the free body diagram for the magnet. And the magnet is attracted towards the fridge. So I'm going to draw a force towards the fridge. And I'm going to label it a magnetic force by the refrigerator on the magnet. Now, once I've taken care of the non-contact forces, the weight and the magnetic force, I ask, what touches the magnet? There's only one thing that touches the magnet, the business card. And I ask, does it push or does it pull? It's not a string, it's not a thread, it's not a rope, it's not a chain, it has to push. Whenever one thing pushes on another, there will always be a normal force. And by normal, we mean perpendicular to this surface between the business card and the magnet. Since the business card is to the left of the magnet, a push is going to be to the right. Okay? And it's going to be perpendicular to that surface. Now, whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. If there's a friction force, it has to point parallel to the surface, which in this case would be up or down. So, do I need a friction force in this diagram? Yes. Oh yeah, because this diagram is going to scream balance. That magnet's not going anywhere. And so I need a friction force. What flavor is it going to be? Static or kinetic? Static. A static friction force by the business card on the magnet. And by Newton's second law, with zero acceleration up or down, this had better be half a newton, if this is half a newton. Okay? Notice I didn't use any static friction formula to get that. I used Newton's second law. Now we go to the formula, or the free body diagram for the business card. The first force I put on any free body diagram is the gravitational force. That's got half the mass, so it's got half the weight. Just a quarter of a newton. Now, are there any magnets in this problem? Yes. Can I put a magnetic force on a paper business card? No. I mean, if you put a paper business card on the table and try to attract it with a magnet, people look at you funny. Okay? So, I'm done with all the non-contact forces. What touches the business card? Well, there's the magnet pushing from the right, and there's the refrigerator pushing from the left. Both of those objects are pushing. Whenever one thing pushes on another, there will always be a normal force. So I'm going to be having a normal force by the magnet on the business card. Well, I knew that had to be there by third law, because the business card was pushing with a normal force to the right on the magnet. By third law, these two forces have to be exactly the same size. Now, when this was on an exam years ago, the most commonly missed force was this force here. It's a static friction force by the magnet on the business card. And I know it's there because of third law. The business card is pushing up on the magnet with a static friction force. By third law, the magnet has to push back. Now pretend it's 2 in the morning and you've just been kicked out of the bar with your friend. Your friend is drunk. You're trying to get your friend to the car. You're pushing up on your friend to get him to the car. What's he doing to you? He's pushing down on you. Okay? He ain't heavy, he's my brother. Okay, now, I take into account the push by the refrigerator. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. Do I need a friction force? You bet I do, because this business card is not accelerating either, so its diagram has to scream balance. So I have to have a static friction force by the refrigerator on the business card, and by Newton's third law, this has to equal that. And by Newton's second law, there's no acceleration up or down, so this has to be 0.75 to balance these two. Okay? And those are the free body diagrams. Now I want you to notice something. If the surface of that refrigerator is perfectly vertical, it's the friction force, and only the friction force, that's keeping it up. In other words, if you could polish the front of that metal refrigerator so smooth that it was frictionless, there would be no magnet, no matter how strong, that you could hold your grades up on that refrigerator with. They would slide down to the floor with an acceleration. Okay, so it's the nooks and crannies between the refrigerator and the business card that are holding things up there.